Hello, good morning everyone. A warm welcome all of you for today's session. This is the last day session. Okay, seventh day of this webinar series on power electronics, recent trends and applications. So, very good morning all of you. It gives me an immense pleasure to introduce our speaker, today's speaker, Dr. Suresh H Jangamashetti, professor in Department of EEE, Basaveshwar College of Engineering, Bagalkot. Our professor is working as professor and HOD in the Department of Electrical and Electronics Engineering, Basaveshwar Engineering College, Bagalkot, with 34 years of teaching and research experience. He obtained MTech in Power Systems and PhD in Wind Energy from IIT Kharagpur. His expertises are in solar wind energy and has 2 pending patents. He has received rupees 160 plus lakhs R&D grants and has 87 plus technical publications with 789 citations, having 10 H index and 13 I10 index. He has established R&D infrastructure in SCADA for distribution, automation, and renewable energy application, and has organized 45 faculty student development programs, attended 59 programs, and delivered more than 150 plus invited talks, webinars. He is a Fulbright alumni, received Fulbright Nehru Visiting Lecture Fellowship to Michigan Technological University, Houston during fall 2011. He is senior member of IEEE, LMISTE, LMISWE, LMSVAK, DMKSCST, and Rotary member. He has been conferred with BVV Sangha's Best Teacher Award in 2018, IEEE PS Bengaluru Chapters Outstanding Engineers Award, VIFA's Lifetime Achievement Award for contribution to wind energy in 2016, Bagalkot Rotary Club's Certificate of Appreciation, Service to Technical Education in 2016, BEC IEEE's Certificate of Appreciation, Service to Technical Education, Lion and Lioness Club, Bagalkot's Human Service rendered in the field of education in 2015, IEEE Bagalkot Section's Outstanding Branch Counselor Award, IEEE Bangalore Section's Technical Publications Award in 2010, IEEE Region's 10th Outstanding Branch Counselor, and presently he is Dean Research and HOD of EEE Basaveshwar Engineering College, Bagalkot. So this is the brief introduction about our speaker, today's speaker. So on behalf of the institute, on behalf of our department, and on behalf of all the participants participating over here, I heartily welcome Dr. Suresh H Jangamashetti for this session in this webinar series, Power Electronics Recent Trends and Applications. Sir, you online, sir? Suresh, sir? Yeah, please unmute, sir. Sir, please take over on the session, sir. I request you to take over on the session, sir.
Sure. You are able to hear me?
Yeah, sir. Your voice, everything is have clarity, sir. You can go ahead, sir. Thank you, sir.
Yeah.
I'm muting, sir.
Yeah. Good morning to all the participants. At the very outset, I would like to thank the institution, Siddhaganga Institute of Technology, SIT, Head of the Department Electrical Engineering, Dr. Rashmi, and the host, Professor Rajiv, and all my colleagues at SIT also, and all participants. Very good morning to you, and good health greetings to you all. Indeed, this is a very interesting topic that the Institute has planned to organize, that is power electronic applications. And today it's the turn for power electronics in wind energy conversion systems. I would be covering today, giving you some introduction about the energy scenario related to wind energy. Quick look at the history. Then we look into the what exactly goes in understanding the electrical power output of wind energy conversion system, and then the role of power electronics in wind energy conversion system. I have to admit, and then I'll be taking question and answers if time permits, or else you can always email me. My experience with wind energy, here I am just going to be more candid in saying very clearly as per the topic, our electronics applications in wind energy. I have not done directly a research in designing any converters or the inverters or working with those. But I do have some experience about understanding what is the role of this, because my core research in wind energy at IIT Kharagpur between 96 to 2000 was mainly focusing on wind data analysis. And finally, I feel very happy to mention that we came out with a very good simulation model as well as a practical model how we can choose or select a wind turbine for any given wind site. So a generic model as well as a software was developed by me. That was under the guidance of Dr. V. Guru Prasad Rao, late Dr. V. Guru Prasad Rao, who guided me through those 4 years. And it was a very good contribution for wind data analysis, which is very essential for installation of wind turbines. How this journey started was in 1995, before I joined for PhD. One executive engineer from KPC, Ganesh Woody, was delivering a seminar in our college. I remember that very well. 95 means still not much developments in the college. Even we did not have smartphones. His seminar was being delivered here because he was looking after the Kapatguda wind farm. And I attended that. I learned there about how a wind turbine works and what it is, and how much power is being generated and all the connectivities. It was in a general talk that was given. But while attending that seminar, I never dreamt that I would be entering into doing research into wind energy. That's the fact. Clear? So that's why anything that comes across during our phase of life, we must look at it in a more positive way. So as I had done at that time, but the same very next year, when I got admitted for research at IIT Kharagpur, and I was given the tasks. So after completion of my award of the degree in 2000, by that time I had done a wonderful work of wind data analysis of almost 104 Indian wind sites, and finally a software package in MATLAB. I had developed interactive software package. It's still with me, but not commercialized, that's for sure. Reason was because I could not find how to convert those MATLAB files into machine independent exe files. If amongst listeners, if there is anybody who says, sir, I can easily convert and make it as a machine independent installable software package, you are always welcome. Over these years, from 2000 till date, it's almost 20 years now, guided its total is 7 PhD theses. Just in May 2020, I had the last one which I have mentioned there. So 7 theses, out of which 3 are directly in wind energy. Others were in hybrid, 2 were in hybrid solar wind. But these 3 I always consider as the ones that contributed. First one was optimum site selection for wind power plant based on financial assessment. Dr. D.R. Joshi, and R.L. Nayak did a very good work in 3-level neutral point clamped voltage source converter for grid connection of wind turbine, short-term wind forecasting model for planning of wind plants and scheduling of power. Recent one, just 2020 May 29. This was awarded. So this is my experience when I am speaking. So you can look at that only in the second thesis, where I was looking into some of the aspects of the power electronics directly used in wind turbines. So quickly, let me start with a brief introduction about wind energy. Well, at one time when wind power in India started somewhere in middle of 80s and late 80s and 90s, it was a big news. Oh, we are going to have wind power generation and all. Late 80s and 90s, we were trying to really work with this, and then we were trying to really implement some of these at the country level. They were all only the wind power plants, that is a demo like wind power plants of very low capacity wind turbines. So I have at least seen from the day I started in 96 till today, I have seen a tremendous change in the technology. So where do we stand globally? If you look at, I'm not going to go much in details, cover up overview it will be, because I know in the audience we have students, we have master degree students, UG as well as master degree students, and some research scholars may be there, and faculty members. So this is a mixed audience. Maybe from industry I have to check. Maybe in the end I will come to know about that. So if you look at that today, the total installed capacity of wind power generation is around 650, 6,000, what is that? 650 gigawatts, we can say. Where India stands, that means it's quite large. The entire India's total power installed capacity is 370 gigawatts. Clear? That's what we should keep. So wind power globally is higher and is sufficient for a country to be run, a country, large country like ours. This is how you can see. Quick look at this, it tells us that there is like this is just from 2013 to 2019 end, you can say. See, this involves financial aspects, this involves job aspects, this involves tells us clearly that we are getting energy from the wind turbine, and technological growth, R&D activities, and so many major players, private as well as public sector investors. So overview, if you see that United States, China, India, then we have European countries there coming into all these installations, manufacturing. So huge amount of activity, and it has become a core sector of power generation nowadays. Most of these are all grid connected power plants, and they are all distributed across the globe. Where you would find all these will be in those places where there is constant or uniform wind velocities continuously flowing for over a period of time. So availability of wind velocity is must, you can say. When it comes to our own country, India wind power installed capacity, if you see, we are around 38 gigawatts as of now, from the sources of MNRE. If you visit MNRE Geodata, you will come to know in detail exactly how the generation. So this shows up to 1920 financial year, from 2004 onwards. Now, if you look at this year-wise installation, year-wise installation is one, and the total installed capacities, and this is every year so much is installed. So previous year to next year, the link will be only that maybe there were large number of investors coming forward, and they all had the technology coming into picture, and government encouragement, subsidies, so many things would be part of this, and also the people who are coming forward. So people had money, they wanted to invest. So if you look at this, 16-17 is a peak, and again you see after that there is a slowdown. Again 19-20 it has picked up. And again, this year, in view of the pandemic, what we are experiencing now, the COVID-19 pandemic, so that definitely will be affecting. So that will come to know at the end of this particular financial year. So actual wind power installation, what was done, and the single black line, what you see is the cumulative. Very interesting, where one can write one essay on this single graph, telling what exactly happened in these years. Was there a change in government? Was there a change in, was there not much of manufacturing and economy slowdown? Was there anything can be thought of in all these? Or the other power generating power generation from other resources was also doing extremely well. We can also relate to that. And last 3 years, we can always know that there is a very good, interesting spike or growth in solar grid connected solar PV power plants also, which is quite easier, you can say, for installation. And maybe that also may have had effect. We don't know. A lot of things will be there, and it is a thought to be really debated on. So the cumulative growth, which you saw in the previous diagram, is shown more clearly in this financial year 18-19, that is year end of 19. Also, you can see it shows 356, and we have this is already it has gone to 370 now. That is 37 gigawatts, 370 megawatts, you can say. Look at the growth here also from 2002 onwards, goes back 2 years earlier. It started from just 1.6 gigawatts to 35 gigawatts is the growth. The increase in percentage from year to year, and from 2002 to 2019, very good information can be drawn. All said and done, India is now the fourth largest investor, or is having the fourth largest installed capacity of wind power generation in the country. Now, as engineers, as prospective job-seeking students, I have to mention this clearly tells us that there are very good job opportunities in core industry, provided you have the knowledge of the technology that is being used in wind power plants. That's what you are. So whether it is manufacturing, whether it is individual components of the wind turbine, or different materials of wind turbine, installation, commissioning, operation, maintenance, you can see, look at all sort of jobs will be there, including R&D, research and development also. Fine. And if you look at the state-wise in our country, let us not bother about our other countries. Let us know about ourselves where these are. Why I'm showing you this? This is where you can always look at these states for the jobs. If you look at here locally, you will be here only. But you need to look where the activity is going on, and with this knowledge, you should be able to face the interviews and tell them, I have some knowledge and I can work for you. That's how it goes on. Clear? So if you look at this, that is the Tamil Nadu, Gujarat, this is 25% of 37.7 gigawatts as of March 2020. Clear? Again, this graph also, statistical information is from MNRE, Government of India. Yeah, I must tell you that India is the only country that we usually tell that is the only country having a ministry for renewable energy. That also we have to keep in mind. Fine. I don't know, maybe some other countries may have joined, but India is having a separate ministry for this. Tamil Nadu, Gujarat, Maharashtra, Karnataka, Rajasthan, Andhra Pradesh, Madhya Pradesh, Telangana, Kerala, and others. Interestingly, when you are listening to this particular information, you have to also keep in mind what is the potential at these states. Clear? So if you look at even in the same order also, the potential is quite larger, but Rajasthan in fact comes with the highest potential, but you find the less amount of energy being converted from wind to electricity. So if you visit the National Institute of Wind Energy with headquarters at Chennai, if you visit their website, they very clearly give you the potential at different heights. You remember, wind velocity varies from ground level to the, as we go higher the altitude. But there are some terrains where it might also decrease. So you need to identify a terrain where we call it as a positive terrain, and it must be increasing. Clear? These will be usually found in places like Muppandal, or you find in Tamil Nadu, all these places. I remember visiting Muppandal. That there are a lot of sites there. That is where the western and eastern Ghats end up. For in these two states, that is Kerala as well as Tamil Nadu, and there is a pass created where very good amount of wind from oceans, usually the monsoon winds, flow through these two passes and go across Tamil Nadu. That's the reason why. Even same case with the Gujarat also, you find Gujarat, Rajasthan, where they have very good passes where medium to higher wind velocities flow. In Karnataka also we do have, but these are because of some of the western Ghats ending up, and where the monsoons flow down, both forward monsoons as well as the reverse monsoon, constant wind velocities also do flow, but the wind velocities are quite lower. That's what you should understand from this graph. Now, if you are looking for where I can go and really do work, you need to look where there is higher wind velocity available, where wind installers also will be looking at setting up their power plants. Major power plant, wind turbine manufacturers as well as wind power plant players are there in the industry, you can say. Quick look into this history. Well, this is what the entire wind energy scenario. You must have a picture of that in mind, because you must know that there is something that we can get from the wind power plants and wind power generation. But you should also know the history, how it has gone through. I'm not going to go in detail. Just in 2 slides, I would like to cover up this particular aspect of the history. Just look at this, observe these slides. See, this somewhere in 15th century, they say something like that, even in 600 BC, or where they started working, they were just using the natural flow of wind for several applications. Maybe there was a lot of water coming into some of the low-lying areas where below sea level water fills up and it has to be thrown out. So no motors, no machines like that. So naturally available, because we know that sailing was being done overseas, no motors, nothing, just how the sail took them, they were going across the sea. That was the application of wind. Clothes, even when you put your clothes outside, if there is wind, along with sunlight, it dries faster. So another application. So like this, you look at this. This is a vertical axis wind turbine way long back. Then they come out for grinding purposes. They were using a horizontal axis wind turbine. Some of you can even make a small model. You have your children in home and sit with them and make one small interesting model, working model only you can make. You need not have to generate electricity or do the grinding work or throw to the water. A lot of these things are antiques now, you don't get to find also. Then in European countries, they started making with brick masonry, and these were not used for electricity generation, but mainly for grinding purposes. And some of the European countries where water used to rush in some of the neap tides, then that water has to be thrown out. They were making use of even these particular, they used to call them as windmills. We don't call them as wind turbines, wind mills, right, for grinding purposes and all. This is a color picture of the same one where you are seeing an artistic view, and this is the actual photograph in European countries. You'll find them more in Denmark, Netherlands, like that. If you happen to visit, do make it a point to visit these things. Clear? But very interesting. These are not destroyed by anybody. Clear? They are still standing there as a they just speak about the history and the mindset of the people, how advanced they were at that time for whatever it was available. They have developed and created. That's what we have to appreciate. And technology started growing, and that is in the modern area, I can say, after 19th century, like that 20th century, where material, machines, industries, metal, all these things were available and they were being used. So at that time, very interestingly, you used to look at the tower, it is called as the lattice tower. Okay. Then finally, you see a tubular tower here. That means it is fully covered. It is usually of some material that is not so heavy, and then it is covered some cladding type metal sheets they used and make it as a tubular. And inside that bottom base, you look at that how big it is, and there can be a small control room or control center with a transformer. Everything will be placed inside this particular tower there. So these two, typically what you find is multi-blade. You see there are four blades has come down to 3 blades, you can say. Ultimately, that is the one which is being used. Then the not electricity generation application, but they were also now doing some other water lifting application. Naturally, it has to do in some remote places where access to electricity was not there. Of course, this is a figure diagram from Gujarat state. I think so. It is from Gujarat state. Now these you don't find. If at all, if they are there, they are only show pieces. Again, it is having a lattice tower, and it is a multi-blade. Not 3 or 4 blades, we call them as multi-blade. Multi-blades will have higher torque, and that's what we have to keep low speed. Now these will have very lower torque, shaft torque. 3-bladed wind turbine. You can see, look at the tower, sleek towers. They were now going up to even 70 to 80 to 100 to 120 meter tall towers you will find with blades of almost around 65 meters in length. You get that. So this is what is the most modern wind turbine, and you can see here how that installation process is going on with the help of a crane. Clear, naturally a tower of 120 meters has to have a crane which can go beyond that. So first they erect the tower, then they use the nacelle, then go and fix up. So the top one, what you see here on the top, is called as a nacelle. These are the blades. I'll be just telling you a quick brief about these also in my further slides. Clear, individual wind turbines now generate electricity maybe up to even 7 megawatts. A single wind turbine, 7 megawatt. Clear, Bagalkot township, you will have around 20 megawatts of power sufficient for town, Bagalkot town, that is not district. Same as even Tumkur town could be having somewhere around 20 to 25 megawatts of power requirement. So 3 or 4 or 5 of such big wind turbines, but is always there that there should be uniform and rated wind velocities which will blow for generation of electricity continuously. Underline the word continuous, because wind is intermittent in nature. We don't know when it comes. It is a natural. We are not going to create a wind to operate this. This is what we have to keep in mind. Typically, when these are all fundamentals, basics we are going. Now we are going to go more a little bit inside into the wind turbines. Typical wind turbine rating I am showing here. So as engineers, you need to look at what rating should these wind turbines should have. This rating is 7 megawatt, single wind turbine. Clear? So when I say wind turbine, the details of those I will just show you in my following slides. The model is S7.0171 Samsung Heavy Industries. Hub height will be the height from the ground to the middle of this particular rotor blades here, center point. That is called as hub. That height is 110 meters. Okay. Rotor diameter, that means from one tip, when it starts rotating in a circular way, so that whole circular rotational area of this swept area, we call it as, it is 171.2 meters. Then cut-in wind velocity, rated and cut out, these I'll be defining you soon, but keep these figures in mind. 3 meters per second, it would start generating electricity, will generate electricity up to 25 meters per second. So 7 megawatt of power output will be given by this when 11.5 meters per second wind velocities are continuously blowing at that place. So this is the power density, blade length, then generator type, permanent magnet generator, speed is 400 RPM, output voltage is around 3300 volts, and converter type. So this is what power electronics we are trying to look at. ABB PCS 6000 millivolts full power converter. So we'll come to know what is a full power converter and the other type of power converters in my presentation today. So this is how, like if you go and ask, you want to really buy a wind turbine, or you want to be investor in that, or you want to be a consultant in that, you need to know what all these are. And looking at this, clearly we should be able to know how it is going to operate. All said and done, we need to have the information about wind velocities which are blowing, which are flowing at a place where you want to install a wind turbine. So these are all very interesting aspects one has to keep in mind, but nothing new. There is nothing new, but you'll be usually using your basic fundamental knowledge to understand this. Basically, we have two types of wind turbines, horizontal axis wind turbine and vertical axis wind turbine. Clear? So you don't get to find these vertical axis wind turbine for the reason of a lot of technical aspects and controlling aspects and operation and maintenance aspects, all that. But they have, both of them have their own advantages. So a horizontal axis wind turbine, these are shown as a offshore, not onshore means on the land. This is offshore. Same can also be installed on the land also. That is onshore. Both will be same, not much difference. Only thing is you will have more wind velocities continuously blowing across the ocean. That's why now offshore wind turbines are becoming very, very popular. And also the capacities of these are quite higher than the ones which are installed on the onshore also. Clear? So when we look at a wind turbine, this is called as the tower. And from the base, you can think of this as water as well as land. Both you can think. From here to the middle of this is called as a hub. So this will be the hub height of the wind turbine. This is the blade length. It is called as the rotor blade. Clear? This is the rotor blade. When normal wind velocities blow, by virtue of the shape of this blade, it will start rotating naturally. Most of you as a child, you have played in your childhood making your own handmade fan, and then you started running around the streets. Children of our age, I'll tell, but modern students don't do all that nowadays. Present day children, okay, if they're doing it, it's really good, maybe in villages and all. So this is where you find this, and it rotates naturally. This is called as swept area. So natural rotation goes on. Same way in vertical axis wind turbine, this is the axis here, and these are the blades here. Clear? Typically, again in horizontal axis, vertical axis, we have 7S rotor wind turbines, and the another is I should not forget. I'm not getting the name. Anyway, any of you can just remind me. 7S rotor and Darius rotor. This one is the Darius rotor. Okay, it's like looks like a egg beater shape, and when it rotates, these blades would be going out, and they'll be fixed here, and this part will be coming down slowly where they're fixed in higher wind velocities. And as the wind velocity is lower, it goes back to the original shape. So a lot of here what happens is the blade material, though done very nicely, in higher wind velocities, applying brakes, and then many times these blades have snatched away. That's why nobody is going in for investing in this, but these continue to work in a more popular way. Clear? That is the one. But for nowadays, for low wind velocities on rooftop and all, these can be very well. Instead of this, they go for 7S rotor wind turbine. Okay. In both cases, you observe that constant or little higher wind velocities are required, not too high wind velocities. Up to 19 meters per second, it's quite good for wind power generation. You can go up to 25 meters per second in larger wind turbines, but still it will be quite dangerous to the tower as well. As you remember, for this to stand, you need guy wires here, but for this, there are no guy wires are used. Entire generating, that is the shaft of this is connected to the gearbox, to the alternator and all that, and wires have to come down and then they are taken to the transformer. But in this case, the entire whatever is, you have to raise up to this height, it will be at the ground level itself, easy to operate. That's the one advantage of vertical axis wind turbine. Going a little bit more deeper into all these wind turbines, when they are rotating, remember there is a mechanical part. So this is the mechanical aspect which rotates. This is the mechanical part which rotates, converts the kinetic energy in the wind through these wind turbine blades to the shaft power. Right, this will be having a shaft. To the shaft of this is rest, everything is connected. So if this shaft is going to have the mechanical power from kinetic energy, the moment you say rotational part and the material, the weight of this, so many things when you consider, that means it can't convert 100% of kinetic energy, power in the wind, to the shaft power. That is where the mechanical engineers come into picture in representation of these wind turbines. Yeah, analysis, you can say, study of them. So it is mathematically as well as practically proved thing that we cannot convert 100% wind energy, but you can convert only 59% of that, 0.59, and it was proved by a scientist called Beds, right? But it is also popularly called as Beds limit. That is called as coefficient of performance. So based on that coefficient of performance of these machines, you can look at this, how they are located. This is the curve beyond which no wind turbine uh, I mean goes for its performance. It will be below this line only. So if somebody comes and tells you my wind turbine is working 80%, then it will be 80% of this 0.59 you should keep in mind. So like that, if you see vertical axis wind turbine, multi-blade wind turbines here, then you get again vertical axis wind turbine. So multi-blade, horizontal axis, you can say. Again, you find a vertical axis wind rotor. After this, you find three-bladed, two-bladed, and single-bladed. Yeah, for experimental purpose, in some places they tried working with single blade. They have tried working with a two blade. I remember if you travel from Belgaum to then Kolhapur National Highway, somewhere after Nidasoshi, you would be finding two blade wind turbines. I remember very well. I should have shown you some pictures which I had taken long back. Two blades were there, but all of them are not. None of them are working. They're just showpiece. I don't know whether they are also removed and newer type are installed. I'm sorry, I don't have the latest update. Somebody who is there can update at the end. Single blade you don't get to find, at least here in our country, but you will find wherever you go. Nowadays, you travel across any highway, any place across the Karnataka state also, you will find this, especially Chitradurga, Davanagere region. Nowadays, even Bijapur district, you will find Bagalkot district. Then you go to any of the Gadag, that is a place, Kapatgudda, first wind power plant of the Karnataka state came there. So you will find all of them as horizontal axis wind turbine. What we need to understand from this is little bit of a mathematics here, which tells about tip speed ratio. Clear? The tip of the rotor blades and its speed of rotation and the velocity of the wind, all three together, that is omega, that's angular velocity here, and all that is going to really tell us how much energy can be converted, or those things we can understand about the torque, you can understand about the speed of rotation. All those things will be represented. So you find that optimally three blade gives very good performance. That's why it is found there. So you have a lower lambda here, then you get the lower coefficient of performance. So rotor power coefficient CP is on the y-axis here. If you look at all this, I'll not go much deeper into these curves. Then only thing I'm showing you this graph, very popular and available in most of the reference. Anybody who writes on wind turbines or wind energy speaks, they will be speaking about this graph. Okay, this is from here we move on to understand exactly how what is the working principle of this, how energy is really converted here. These are the rotor blades which are on the shaft here, free flowing. It is not fixed or nothing like that. But you can also control the axis of rotation of this. That is not done by wind. It is done, by automatic controllers of this here. Okay, this is what it is. Then we find the horizontal axis. I'll just take just 1 second break here. I'm getting a call. I'll quickly say and come back to you. Please, I seek your excuse. Sir, good morning. Yeah, Raju, good morning. Hello. ಹೇಳ್ರಿ ಕೆಲಸ ಬರುದಲ್ಲ ಸರ್, ಬಂದಿಲ್ರಿ. ಇಲ್ರಿ ಬಂದಿಲ್ಲ. No, sir. It is not being brought now at present. ಸರ್ ಅದೊಂದು ನಾ ಡಿಸ್ಕಸ್ ಮಾಡ್ತೀನಿ ರಾಜು ಬಂದ ಐ ಆಮ್ ಡೆಲಿವರಿಂಗ್ ಆನ್ ವೆಬಿನಾರ್. ಇಫ್ ಯು ಎಕ್ಸ್ಕ್ಯೂಸ್ ಮೀ ಪ್ಲೀಸ್. ರಾಜು, ನಾ ಬರ್ತೀನಿ ರಾಜು. ಸಾರಿ. Yeah, extremely sorry. It was call from principal, so I had to attend. Fine. Professor Rajiv, you are able to hear me, no? No problem. Professor Rajiv, or anybody from the audience, can I know you are able to hear me?
Yes, sir. You are audible, sir.
Yeah, thank you. Thanks a lot. Because when everything is quite on the other side, sometimes we have our own doubts. Okay, thanks a lot. Fine. So continuing with this particular how exactly this power conversion takes place, you look at this diagram here where this lift and drag. Okay, there is huge mathematics around this also. Lot of modeling or all that can also be done. Okay, so when the wind blows across this particular blade here on the top portion as well as bottom portion, it will have a lower pressure at the bottom and higher pressure at the bottom and lower on the top. So it will have a lift action from this and drag action on the other side. As it is fixed here, so the drag one will have a rotational movement here. That's how what lift and drag to. Drag will be towards the tower, lift will be in the air. So these two forces are the resultant force of these two will make this particular blade to rotate. That's what you have to understand. So whatever is the magnitude of wind velocity that is blowing and at what angle to this particular hub is this wind blade located. So remember, older wind turbines were fixed. This you could not control. Modern wind turbines you can control. That means in the varying wind velocities you can also vary the pitch angle. Then you can control the rotation of this rotor blade. So this turbine is very important. This is the turbine for you. That's why the name is wind turbine. So in wind, this turbine rotates in the wind. So later on is the shaft. Now this is, you find a tail provided here. This is a small wind turbine with a lattice tower. So to tell this little bit in a better way, so at the bottom you have the higher force coming here, On the top which goes, it will be lower when the winds blow here, so it will experience a lift. Drag will be towards, so you should always try to see that the drag is minimum, because it should not go and hit the tower or cause vibration to the tower, so damage should not be caused. So that care is taken when rotor blades are designed. Okay, that's what we have to keep in. I'll not go, because I usually teach one full chapter on this particular lift and drag, and how much power is converted, how much torque is produced, and from that torque, shaft torque, how we go ahead with the alternator, all that. Okay, that's it. Now what we are interested is the amount of wind which is blowing is that disk which is passing across this. I'm sure you all of you are viewing. I'll go back and come here. You can see this. See the wind represented by the disk of representative wind, what you are seeing. Now you can see the rotor blades and the amount of wind velocity only which cuts across the tips of these and all that, the entire area, only that is the kinetic energy of the wind, which will be converted into shaft power. If whatever is the wind velocity blowing here or above, that has nothing to do. That's what we have to keep in mind. But the winds which are around can be slightly disturbed, and for how long it will be disturbed, that also has to be kept in mind. That comes in wind farm location, that is locating the wind turbine designing aspect. That is again a separate aspect which I am not going to cover here. So what I am interested to here is how much of wind power is there in this wind velocities which are blowing at different places. I mentioned earlier that from the ground here to the top of this, so as you go up the altitude, wind velocities increase. So you should look for a terrain which will have a wind velocity increasing. Okay, because the tower height can be up to say 30 meters to 60 meters, up to 70 or 80 or 100 or 110, anything it can be. So if at that tower height, if you are not assessed these wind velocities, that means you have to measure the wind velocities to know about that. And using all the statistical methods, you have to estimate. That was my work. My contribution to research was, so for what all wind velocities are blowing at different heights, usually from hub height, we take it as a standard. Assume that throughout this length, in that entire area, it will be same. If you look at 60 meters on the other side and 60 meters this side, and that definitely in that 30 meters length there, the wind velocities can be varying continuously. But for all the study and analytical purpose, we say that it is flowing constantly across this. So this is how the power in the wind, and a very interesting derivation can be done with basic fundamentals, which is say power in the wind is half rho A V cube. Okay, rho is the air density at a location. A is the cross-sectional area of whatever the wind turbine you presume is going to be installed. Okay, it can be continuously changing, not when it is installed, but for analysis purposes. And so for given wind turbine, these two and a wind site, these two are usually taken, rho and A, kg per meter cube, and cross-sectional meter square, and velocity meters per second, meters per second velocity, right? So by through derivation, you will come to know that power in the wind is proportional to half rho A V cube. Clear? So assuming for any given site, rho and A remain same, so power in the wind would vary in the cubic times of the velocity whatever is available. So this for us, it led to taking, instead of taking arithmetic mean of these wind velocities, we can always take cubic mean cube root of this wind velocities and then go for wind data analysis. That's what. And finally, applying all the dimensions, you will come to know that the power output also will be in watts. You will be able to get that correctly. Clear? That is a proven thing. So for all said and done, quickly let us see the cubic mean cube root of the wind velocities is determined in this way, gets meters per second. Then you have the standard deviation, very much required to know how the from the mean how much variation is there for this. Statistical methods like Weibull probability density functions, which have two parameters, shape and scale parameter, represent the continuously varying wind velocities over a period of time. Remember, it is not instantaneous. You have to take it for over a period of time. So 1 year, if you take the entire wind data, you will have a huge amount of wind velocities recorded. So that has to be represented and analyzed. And for wherever the data is of lower duration measurement, then you can use Rayleigh probability density function. These are I'm just showing you, not going much deeper. Anybody who requires any clarification later on, you can always ask for that and are available. Now quickly let us look at the electrical power output of a wind turbine. That's what most of us, I am presuming, are electrical engineers here. So we need to understand about the electrical power output, and there is a mathematical expression and derivation which I will quickly run through. When we represent wind energy conversion system, now this is where we have two aspects, mechanical aspect as well as the electrical aspects. Clear? So till the generator, we have a turbine. From the turbine, we have a gearbox. And from the gear, that is called as a transmission, and from there it goes to the generator or the alternator shaft. So shaft of this gearbox, slow speed, then high speed, you have the alternator. So this alternator, by the rotation of this wind turbine, would start generating electricity. It can be a synchronous generator, it can be a DC generator, it can be an induction generator. So knowledge about electrical machines is purely here, which I am not going to go into that. So once you get this, so you know that this is varying. Naturally, shaft power, what we get, depending upon the controllers used, it would be varying. Then you get the rotor speed from this gearbox has to be kept a little of a same or higher. 1500 RPM, we know that. 2000 RPM it goes, 700 RPM it will be there. So that range of depending upon the type of alternator used here, then you can have the output from here. Now question is, can I connect this output? Output is always AC, you must remember, except for DC generator. So here DC generators for a given rating, the size grows very large and heavier, so they don't use them. Clear? For small applications, small wind turbines, you can always use. Even in small also, PMSG machines are used and gives you AC output. Now if I want this to go to either AC load or the grid, most often it is always the grid. Now grid requires constant frequency, voltage, then the phase, everything has to be maintained. It has to be, that means it must be synchronized to this grid. Voltage levels we have to synchronize, the frequency you have to synchronize, the phase angles you have to synchronize. So that synchronizing aspect for this varying continuously, different variable frequency, then you get constant here. So this is done by what are called the power converters. Clear? So these power convert, this is where your power electronics comes into picture. So AC is converted to DC, DC is converted to AC of required frequency, which is required for the naturally Indian grids. We have 50 hertz here. Clear? At what different voltage levels, 11 kV or 33 kV grid, or you may have a 110 kV grid or 440 grid or 760 grid, like that, depending upon the voltage levels here, what you convert and get it to that level. So naturally for a 7 megawatt wind turbine here, you are going to have think of this particular alternator, 7 megawatt it will be generating at any one instant of time when rated wind velocities are blowing. So from this, naturally one can understand or think of the capacity or the size of the power that this converter has to handle. And that is where the role of power electronic engineers comes into picture. Clear? Showing the same thing in another form in the block diagram I am trying to show you here. Wind speed, it will have the turbine pitch and so controllers will be seeing. Then you have the generator side, you will have the transmission efficiency of mechanical turbine structure, the electrical generator, electrical interface. So efficiencies of all would be required or is necessary when I want to know how much power I am going to get at this point. So these studies. My core area was totally involved in the wind data analysis, and I tried finding that if you give me any wind site data, hourly wind velocity is measured over a period of 1 year, then I will clearly tell you which wind turbine has to be installed at that place. Depending upon the rating, all these things, selection design has to be done there. That is my expertise. So quickly, if you look at this particular block diagram of now trying to find the electrical power output, a clear block diagram is given here. Power in the wind, then you get the shaft power, that is a mechanical power. Then from the gearbox, you get the transmission power output. Then you get the electrical power output. So if I relate them to coefficient of performance for the turbine, transmission efficiency, gearbox efficiency, generator efficiency, they're quite definitely in the range of 80 to 85, 85 to 90, 90 to 95, like that. So in that way. So what is the other parameter? That is the omega, that is the angular velocity of the turbine, then efficiency of this gearbox, and then finally the electrical aspects here. So this whole thing, if I start writing my equation from the electrical power output going backwards, it looks something like this. Electrical power, or you can start from here, PW, right? And my mechanical power will be, if we coefficient of performance is PW. Turbine, transmission power will be PM PW into CP into efficiency. Then electrical power will be PT PM this into the respective coefficients and efficiency. That's what is shown here in this slide. Electrical power output, I am saying electrical, average electrical, that is at any one wind velocity, electrical power, if you put whatever is the data available. In this coefficient of performance, already we have seen that depends upon the tip speed ratio and the blade pitch angle. Okay, then efficiency of the transmission, generator, power in the wind. So ultimately, for any given wind turbine generator, at for any one wind velocity, if you want to take, so this has got a value, these all have got some values, and this is also fixed. Finally, it will be the wind velocity. So wind data analysis cannot be neglected. So only if you have analyzed the wind velocity correctly here, you'll be able to estimate the very close value of a electrical power output, which is shown here in the remaining slides. So at any rated wind velocity, the turbine is having 10 meters per second as a rated wind velocity. For all the rated quantities, you can also get a single value. But for over a range of values that are available, I'll not go much deeper into this. The representation will be between less than cut-in wind velocity, no power generation, above cut-out wind velocity, no power generation. So these two have to be very well analyzed and derived for them, and have to be represented for the analysis, which I went further in mathematically deriving this and came out with capacity factor is one quantity parameter used for performance analysis, and basically the final representation of capacity power is shown in this fashion. Capacity factor, this equation is little has a lot of things. Only one point what I want you all to look at is, look at this VR by C, VR by C, then VC by C also can be written in VR by C, VF by C also can be written in the form of VR by C. So this all can be written in the form of VR by C. Then you can have a graph, very interesting study for site matching of wind turbines, which I am not going to take here. So with this, usually whenever wind turbine is thought of understanding, or you want to know its performance analysis, then the performance analysis is seen with capacity factor. Okay, so understand this capacity factor very clearly. Energy production in 1 year divided by power rating of that, and because that rating also has to be taken for over a same period of time, which gives you the capacity factor. That's what we have to keep in mind for understanding the wind turbine. So this entire range of power that is being generated by a wind turbine can very nicely represent it. See, we know that this is the average electrical power output at any given wind site, which would rise in this way and is 0 to infinity, and that is P into that is function of velocity, average electrical power function of velocity. F of V can be any statistical method of representing continuously varying wind velocity. The popularly used is for wind data analysis is the Weibull two-parameter Weibull density function. Rayleigh function also used. So for those of you who would like to take it as a challenge, as a research, you can continue to work on this F of V representation of the wind data. Then this power is this ಅದರೊಳಗಿನ ಗಾಡಿ ಒಳಗೆ ಬೇರೆ ಏನ್ರ ಇಟ್ಟಿದ್ರೆ ತಕ್ಕೋ. So this one is the region 1 where it is less, wind velocities are blowing less than the cut-in wind velocities. These are three important characteristic features of a wind turbine, right? Wind turbine generator. Whenever you go there, first thing you ask is what is cut-in wind speed, rated wind speed, and cut-out wind speed. Fine. So for these three, between the cut-in and the cut-out wind speed, the electrical power generation takes place. For all the wind velocities which are below and above, no electricity power generation takes place. So this is the equation there. So when variation is from cut-in to the rated wind velocity, representation is average electrical power output will be in Vc to Vr half rho A, this whole thing here. Now when this representation is done, the people are still working on understanding these particular trying to come out with newer representation of mathematical models here. You can always try how you want to represent this part. Okay, here from rated to the cutout wind velocity, it is again Vf to Vr to Vf. You look at this curve becoming flat till up to some velocity. That means up to some velocities after the crossing of rated wind velocity is by controllers, right? Purely the electronic controllers take charge, and then the pitch blade is controlled such that you get, even in stalled controlled also, it was by natural, it was being done with some controlling the speed there. And finally the cutout wind velocity, no power generation takes place between this range of wind velocity above Vf, we can say. So understanding this all have to be very well analyzed. I showed you the capacity factor, how you find. That's how you go ahead to calculate the performance of a wind turbine. Okay, this is all about it is a big subject in itself, but I have tried to put it across to the audience, saying what wind energy is, what is its history, and how do we look at the wind data, how much electricity can be generated, what type of wind turbines are there, and how do we use them, which one should be used. Clear? And while telling, I just mentioned very clearly and a few aspects about power electronics, where it is used. Now from now on, I am going to really take you into the power electronics. Frankly speaking, I have not designed any of these converters, but we only know that such converters exist and how do they function. In that aspect, I am going to show you this. Quite interesting for those of you who are in power electronics, and a lot of new type of converters can be developed and designed. As of now, the knowledge of power electronics for us is that we know power electronics as a subject, which is they are popularly as electrical engineers, we use them in drives. The moment we say electrical drives, then there is power electronics involved in that. You want to have any electric vehicles, again we think of power electronics in that. Right. So mainly these, so wherever, even if you think of solar energy, which is a DC in nature, but I want it to be connected to grid in AC, look at that, again power electronics is required. So mainly you have studied what a DC to DC converter is, you have studied what is DC to AC inverter is, their design, rating, all this is taught at the undergraduate level itself. From there, if you had a little apprehension about power electronics, just like me, I did not go more deeper into power electronics, definitely, but we do know what these devices and how they are and how they work. Okay, why do we require power electronics when we think here in this case? We should keep in mind the power that is generated from wind turbines. Most of it goes to grid, and if it has to be connected to grid, I mentioned very clearly that it should be conditioned power. That means it must have constant frequency of the grid. We should have the phase matching, then we should have voltage matching. That has to be taken care. But wind turbines don't give output directly the way a grid requires. Clear? So there we have two types of wind turbines: fixed speed wind turbine and variable speed wind turbine. Clear? I have mentioned briefly about the tip speed ratio, then coefficient of performance I have mentioned. But here, for varying wind velocities, in a varying wind velocities, how these turbines, that is rotor rotates, you have to see, and accordingly you'll be selecting your alternator. Generator selection is parallel to that, whether I'm going to use a induction generator of squirrel cage type or wound rotor type, or I'm going to use a synchronous generator, I'm going to use a permanent magnet synchronous generator. So for these generators, which shaft of which type of turbine I am connecting is the question. So you would be connecting maybe a fixed speed, means that your rotor blades do not have pitch controlling. So over a range of wind velocities, this will start generating electricity, and it will continue to increase as the wind velocities increase, and after some time again the cut in and cut out braking aspects will be there in both type of wind turbines. So this fixed speed we represent, say somewhere it is fixed speed, means it is always maintained, it will try to pick up a constant TV Q U what you see at these points. So as the wind velocities change, you would be getting the power output, but you would not be getting the optimum power output. But in variable speed wind turbines, they make use of what is called as MPPT control scheme. Clear? This MPPT control scheme means it will look at the wind velocity, what wind velocities are blowing, and then it will try to give a signal to the rotor blades for pitch controlling. So that's how you will have the, you can look at this graph PQRS. So it is operating at the higher wind velocities at those where the turbine is rated for. So it will work over a range of optimum wind velocities. Now the output of both, in both cases, is not fixed. It is varying continuously, and definitely having its own frequency of output for which it is generating. That is, it is your generator will be rotating at 1500 or 2000 or even lower. So there will be a range of speeds which it will be at which it will be generate. Yeah, Rajiv, not able to hear? Hello? Okay. You'll be telling me, no? Yeah. Yeah, audience outside SIT Tumkur, you are able to hear?
Yes, sir.
Yeah. Okay, I understand. Yeah, for all the audience outside SIT Tumkur, there is some issue of internet at the host point. So they will just tell me when I should start. Okay. ಅದು ನಿಮಗೂ for yeah, Rajiv, you are back.
Yes, sir.
Yeah.
Yeah, you can continue from where you have left, sir.
Yeah. Okay. Yeah. Fine. Sure. Presentation is here. Just confirm me if you are able to see my slides.
Okay, sir. You share, sir.
You are able to see now?
Yeah, make it full screen, sir.
It is full screen.
Now it's displaying properly.
Okay.
Yeah, it's fine, sir. Your voice is also fine.
Okay.
Please continue, sir, from where you have left.
Yeah. I was mentioning power electronics is required for the simple reason of the type of power required for the grid and also for the type of wind turbines we are using. Clear? So I mentioned two types: fixed speed and the variable speed. We can have a look at how the wind energy conversion system would look like when we make use of a squirrel cage induction generator. Typical like that, you find a lot of topologies available. The ones which I was able to access through some of the papers as well as the representation I am showing you here. So you have the wind turbine and gearbox, the squirrel cage induction generator. One has to understand the functioning of a squirrel cage generator, its construction principle, everything. You all know that they require some reactive power for starting. In case of SCIG, they do make use of a capacitor bank for providing the required reactive power to this ACIG for power generation, and then it is connected through a transformer to the grid. Okay? This is a fixed speed. That means that you will not be able to have, you will not be having any control over the turbine here, except braking. Secondly, scheme of variable speed concept with W-fed induction generator. So DFIGs are very popularly used in wind wind turbines, that is wind turbine generators or wind energy conversion system. Very popularly used. Only thing is that from DFIZ we should know you can feed the grid from a stator side as well as the rotor side. So from the rotor they have a converter here and then bring it back and both are fed. So there is more flexibility and continuity of the power flow to the grid, and you get whatever the frequency that is required. From here, the other flexibility is here that the turbine rotor blades, that pitch angle control can be done. That means you can, as the wind velocities continue to change, you can bring in same speed in this by varying the pitch angle of this. Okay, so that will be done here. So naturally you will be able to. Now gearboxes are popularly used in most of the wind turbine. Of late some are coming without gearbox also. I'll show you one type of wind energy conversion system, how it is done there. So finally, what we tell is power electronics and wind energy converters, conversion systems. Mainly we have the converters, and these converters are two types. One is the grid commutated and self-commutated. Clear? So many of you who have undergone the course in HVDC, you know there are all high power HVDC links which they use, and it's one of the definitely very expensive, but as compared to the long distance transmission lines and all, these HVDC links will provide a better and a stable connectivity for power transmission. They are used in that. You also know what type of devices, everything they are using. Now the other one is a self-committed, used for grid connection of wind energy conversion system. It is not that a self-committed would not be used for grid connected, but here the popularly the self-committed are used in wind energy conversion system. So they make use of PWM control, high switching frequency, higher harmonics, but can be controlled with the filters and all. Very flexible and nice to use also. Design also can be are done nowadays for smaller wind turbines wherever it is required. So what are these power electronic devices used here? Are the insulated gate bipolar transistor IGBTs, MOSFETs, integrated gate commutated thyristor IGCT, MOS gate thyristors, and silicon carbide FETs. You know the technology, how it has changed from the first transistor to the thyristors to the again these high power thyristors or transistors, what we call. So all of them play a very key role in this, and the technology is the best, and work continues to go on in this, because that semiconductor material now again they are now going for silicon carbide materials, all that they are working on this. Clear? So these are the devices used. You know their working, functioning, all that, their controlling, all that we have to keep in mind. So here is one typical power electronic converter, voltage source converter, which is shown here. Now, if you ask me more details in this, it is very difficult, but a converter that is used, I am trying to just expose you or show you. And those of you are already in this particular area of working, well, it will be more familiar. Those if you are not working, definitely you can think about this. So they make use of IGBTs, and you know about these power thyristors and power transistors, which they use, handle huge amount of current, and that controlling of that current is of very important. And whenever the switching takes place, you know what happens there. So they try to get and all these analysis of these individually representing the simulation model, actual model, their outputs, and how pure is the sine wave, all that has to be kept in mind for grid connectivity. Multi-level inverters, of course, my second scholar, he worked on multi-level inverters. Again, a lot of work was done and submitted by him. We have 3-level neutral point clamped VSC and 3-level flying capacitor VSC. These are the two types of again voltage source converters that are employed. Not that all are employed, depending upon the type of you have to keep in mind whether it is generator controlled or grid controlled, and what kind is used has to be kept in mind. Only thing is this power electronic in fact it decouples the grid very systematically, decouples and connects it and disconnects it in a perfect way. Another very important thing we have to also keep in mind is that there will be a requirement of reactive power for the wind turbines. You know, that is another major study which is being complained by many grid operators, saying that they would always take the reactive power, and even both have to be balanced in any grid system. Remember, grid connected AC grids, and if anything is drawn in excess or pumped in excess, is going to cause instability. That also has to be kept in mind. So those controlling also will be very good through these power electronic controller converters. There is also what is called as a matrix converter, most often used for these particular fixed type of wind energy converters, as well as variable type of converters, matrix converter. Then we look into the fixed speed wind energy conversion with a power electronic soft starter. You know what exactly is to be controlled between a rotor and a transformer and to the grid is the amount of power that flows, the very huge amount of power, high currents will be flowing. That has to be very well interrupted or converted into AC. That has to be kept in mind. So first AC to DC, DC to AC. This part is done in this. Soft starter is nothing but it is a current controlling device which will be used here. Then we go ahead with the wound rotor induction generator with rotor resistance converter, is popularly called as dynamic slip control. Now you see from a simple fixed speed to you go to a variable speed. When you go, how the power electronic aspects change here. Clear? So here they make use of the power electronic comes into the rotor side, and the other one is directly it goes to the grid, and the exchange of requirement of reactive power of the wound rotor is met by the stator side, which is connected to the grid. So this way doubly fed induction generators have found more application, are more popularly used in the modern wind turbines. On the other side I am not showing, that is the turbine where the controller also is connected to these for pitch controlling. That also this side pitch controlling, for that again the input from the wind speeds goes back to this controlling the speed of the rotors by varying the pitch. Then another one is a variable speed wind energy conversion system with the DFIG. You can see the diagram here. The DFIG connected, and you also have the shaft control of the rotor, these controllers, and that's what I can say. I don't know. The controllers for the converters are given using a PWM, and you get all the feedback from the other side. And then the connections are made. Then I mentioned at the beginning showing one diagram, wind energy conversion systems with full-scale power converters. Okay, these full-scale power converters will be doing both activities. Okay, it is that is providing reactive power, real power, and then AC to DC, DC to AC. Everything goes on in this. So in the earlier you saw it was only on the stator side. Now it is being done in both sides. So it will be an entire unit taking care of the complete connectivity to the grid here from synchronous generator. Now this is mainly with the full scale is taken with synchronous generators, where permanent magnet synchronous generators they make use of. Clear. So another, this is induction generator with gearbox, induction synchronous generator with gearbox. Then also we have one more without gearbox. So this without gearbox is the latest or the most recent or the modern wind turbines, where I remember Enercon implementing these gearless. They used to call them as gearless wind turbines. And that's what it is. Okay, the now finally with this, I think so. These are the type. Now, how these ratings would look like? Typical ratings of these. I have tried showing here. A standalone wind turbine generator with a permanent magnet synchronous generator. A system configuration. Rated power is 2 kilowatt. Rated voltage frequency is 120 volts for 50 hertz. 17 amperes of current it has to handle. The internal this is for analysis purposes. This data will be required and is taken. The reference I have given at the bottom from where this data is used. This is another standalone wind turbine generator. The earlier ones we saw were all grid connected. This will be connected to some typical loads, small rated loads that can be used. Is here shown here. Most often the knowledge of electrical machines and power electronics is required to take up simulation of these particular converters. Specification of this system, which you saw, is a 7.5 kilowatt. It is okay. All the data is VFC parameters are also given. VSC ratings 8.2 kVA, and VSC rating without ECs also is shown here. Then a standalone wind turbine generator with the PMSG system configuration, you can see it is for a machine. These are all the ratings that I'm giving. We did some small simple work on this. So there we required these specifications. I'm showing in all that. And then we have in one of the papers where they of course referred my first IEEE transaction paper. This analyzed very nicely. You can always refer to this paper, those of you who would like to really work with. Wind turbine specification, and then PMHG specification, and the rectifier what was used is also shown here in this particular diagram. So these are all can be again most of them make use of MATLAB for to develop a simulation model of this, and that's how a lot of work has been done and is also going on in this particular area. Clear. This is how power electronics, mainly for decoupling and this coupling of the generator, and the power electronics change with respect to the type of speed of the wind turbine, variable speed or fixed speed, and accordingly the selections change here. So it is not fixed. So even if I have to make an in-depth presentation, any one type I have to go in depth for presenting. So finally, to summarize, knowledge of wind data analysis, wind turbine parameters, and type of generator used is vital for design of power converters for wind energy, power converters of wind energy conversion systems. It can be or for wind energy conversion system. Either way, this is my summary of this entire presentation, because even if you want to design power converters, what I'm actually trying to tell is wind data analysis, wind turbine parameters, type of generator is must say knowledge in that is required. So I have tried to cover all the three types and then take you through the power converters. Fine. So this is my contact in case if you have any queries you would like to make, or want to do some small projects or work with me. Thank you very much for your patience hearing. I don't know how much impact I have made on you for this particular presentation. If there are any questions, definitely I would be willing to take questions, or you want to see some of the slides again, I can show you and explain. So for the rest of the time before we meet or discuss, stay safe, healthy, and jolly from my side. Thank you. Uh, Rajiv?
Yes, sir.
Yeah, that's what I have come at the end. Should I keep the presentation? If there are questions, I
Let it
can
be,
answer.
let it be like that only, sir.
Okay, okay.
Uh, Hello, participants. If you have any queries in between, or if you want to ask something to professor, something to our professor, you can unmute yourself and you can contact our sir. If you have any queries, like in field of, if you want to do some research in wind energy area, or those UG students, if you have any uh, doubts in wind energy conversion system, you can ask our PG students who wants to do their PG projects or anything if you have. And also in between the presentation, if you have come across with any doubts, you can ask. Okay, or you can put it in chat box also, or you can directly contact to suresh.j@ieee.org, what sir has given on the end slide.
Hello,
Okay, anyone?
hello,
Okay.
May I introduce yourself? Who is
hello,
who
sir.
is?
Hello, sir. My name is Kishore, sir.
Yeah, Kishore, go ahead.
I am first year engineering student, which is studying in SIT only.
Hmm.
Sir, my doubt is in now at Tumkur, the 19 to 20 kilometer per hour is the wind velocity.
Okay, go ahead.
Which generator have to use, sir? No, for
Yeah.
output of getting a 230 volts of 50 hertz.
230 volts, 50 hertz, you would usually prefer to have a small wind turbine, but you won't get directly 230 volts. Fine. So
Yes,
you'll
sir.
have to see each of these are components. A turbine is a separate component, and along with that, in the turbine, you'll also have that is wind turbine. You'll have the alternator. So you need to look for the specifications of a wind turbine which will give that much of power. So exactly if you want 230 volts 50 hertz, then you have to sit down for a lengthy designing. So and your 19 kilometers per hour convert it into meters per second, and then accordingly we'll be able to suggest you. And it has to be measured over a period of time, at least for 6 months to 1 year. This wind data has to be measured. It will be continuously varying. Okay, to put it in a nutshell, if you are having very good wind velocities for over a period of at least 8 months in a year, then it is always advisable to go for investing in wind power generation. Is that fine? Clear, Kishore? I
Yes, sir.
appreciate you in first year you are having this interest. I really appreciate. But you need to take a small course on wind energy so that at least you'll be able to start making some calculation, measuring wind velocities, and then going for a selection of wind turbines. Wind turbines usually are readily available, but not just like we go and buy any other commodity in the market. Most often they are manufactured against a large order, or else whichever is available, or you'll have to make your own by taking different components. Is that fine?
Yes, sir.
Suresh sir,
Having another
Yeah, yeah,
Suresh sir,
doubt.
yeah, yeah,
Suresh sir, Rajiv here.
yeah.
Kishore,
Yes, sir.
Kishore, you there online?
Yes, sir.
I would like to inform you that we have a prototype of
Yeah, yeah, it
wind,
is there.
wind turbine
Sorry,
in our college. Just
yes, it is
arrived
there.
some week back. One
Yes,
Hmm.
sir.
week back, we just arrived. Okay, they have commissioned also. We have 15 HP motor. From that, we are blowing it, and we have a horizontal wind turbine, and the total power electronic controller for charge controller, inverter. At ultimately at the output, we will be lighting up a few lamps, and its capacity of 480 watts. 480 watts output at 230 volt 50 hertz at the output, and we are driving it by a VFD drive. Okay, whenever you are free, Kishore, you can come, or after this pandemic situation, after the restart of our college, you can come. It's at the 4th floor of IM building. Okay, we have commissioned it, renewable energy lab with the prototype of solar PV and as well the wind energy. Okay, you can come and see how it will be and working and all. I can explain you there. Okay.
And also, I remember your in your department they demonstrated another small tabletop wind turbine when I had come there.
Yeah, sir.
Yes,
One
sir.
small,
That
small. We have to fit
Siddhivanga
into Mutt
Mattas
exhibitions
exhibition.
also to
Yes, sir.
give awareness to
Yeah,
the local area
correct.
people also.
Beyond that,
One small prototype is there, sir. Very
yeah,
small. Just
yeah,
one LED will be glowing from that.
yeah, true.
Sir, and having another doubt, in your presentation, yes, DC AC is converted to DC, and then a small capacitor is placed between the AC DC to DC to AC
Yeah,
uh, near the gearbox, sir.
yeah.
What is the use of converting that much AC to DC to again to DC to AC, sir?
Yeah, yeah. And this many of your department faculty definitely they'll be able to explain you. So from my side, I would like to tell you that output of any generator that is connected to the shaft of the wind turbine, it is not constant or same always. It is continuously varying. Okay, this is one thing you have to keep in mind. And naturally, the varying power output is not suitable for connecting it to the grid, or even if you want to connect it to the load also, as per the load rating you need to see that it is same. Now this is AC. Now if you want to condition any this particular AC
Any doubt?
to a required frequency, you need to have a rectifier. First convert that AC to DC, and again from DC to AC using your another inverter which has got your thyristor controlled circuits. So there you will be able to have get the frequency of power that you want. Power with the required frequency you can get it. Now, the role of this capacitor, our power electronics engineers will explain better. But in standalone systems, this capacitor is required to provide the required reactive power to the induction generator. So for that, you need to understand in detail how an induction generator works. Is that fine? And other capacitor, wherever it is used either for some filter purposes and some activities in the rectifier. Fine. I hope I am correct, Rajiv.
Sir, what is this, sir?
Yeah, no.
Okay, Kishore, I want to mention one thing. You are in second semester. It's a very basic question you have asked. And in third semester, when you come to third semester, there's a subject called electric power generation. There is a course. Okay, in that electric power generation course, you will have wind energy conversion system. And also in sixth semester or fourth or fifth, in between, you will have synchronous generators and other power system. There you will learn the synchronization, why we have to make grid integration and all. And then in power electronics, again you'll be learning why this stages of conversion is needed. Again, AC to DC, DC to AC, and then you are connecting it to the infinite grid. So why these will be done and all, you will be learning there. And also at the seventh semester, there is an elective solar and wind energy conversion system. We have introduced that elective. You can learn in detail about this. Okay, Kishore.
Yes, sir. Yes, sir. Thank you, sir.
In detail about this, and it's a very beginner. It's a question like very beginner, and our Suresh sir has explained it in a very convincing way to a beginner like you. Okay, that's what we can do it here. It's a again it's you have to go in deep into it after taking this course. That's what Suresh sir told. You had to take a course first in wind energy conversion system. Okay.
Yes, sir. Yes, sir. Thank you, sir.
Okay, nice, Kishore. Nice. Your interest is good.
Anybody else? Anybody wants to
Anybody
ask
else?
a question? Let me know.
Anybody else?
Yeah, I think so. If there are no questions, can we?
Yeah, we can conclude it, sir. Sir,
Yeah.
Suresh sir, it was a very informative. You have tried your best to shed some light on the wind energy conversion system and to extend our knowledge in the area of this renewables and the scope for power electronics as well in the wind energy data analysis and how to decide and all. So it was quite interesting. Those who wish to take up renewable energy system as a area of study, this session was very helpful. And profusely we express our gratitude on behalf of our institute and on behalf of the department, on behalf of all the participants. I thank you, and we look forward you to be connected with us and motivate the youngsters like us in the like this in the coming upcoming plans of our department in webinars or in FDPs or in
Definitely.
short-term courses, workshops like this, sir. I hope
Okay.
to. I wish to see you again like this by connecting with us, sir.
Yeah.
And for
It
your
will always be good to speak to interested audience in any of this wind analysis and wind related or even solar applications. They can, for
yeah,
SIP, I need not have to tell anything. Okay.
yeah. Yeah, sir.
Okay.
Thank you
Yeah.
once
Thank
again.
you.
Thanks a lot for the session. It's a concluding session of this webinar.
Yeah.
It given a new light and new glory to this webinar for ending this
Okay.
webinar series by your talk,
Okay. Thank you.
professor like you. Thank you,
Thanks.
sir. Thank
Yeah.
you very
Okay.
much.
Okay.
See you, sir.
Yeah.
All the parties, I require. I want to appeal at all the participants. Okay, now we are concluding. We are at the ending stage of this webinar series. I profusely thank you. Thanks all the participants who have participated here with all the interest from far distances and all taking registration over here. And regarding this feedback form of the overall 1 week webinar series, I will be sharing the link of feedback in the group. Okay, please fill it and share it to me, and it will be active for another 2 days. And accordingly, the certificates will be e-certificates will be issued through your email address. Okay, whatever the email address that you have given while registering. Okay, hope you people have enjoyed and something knowledge in the area of power electronics, and you have got motivated to make some extending your knowledge in the area of power electronics. Thank you very much, all of you, for participating actively here. And if any webinars are kind of things, if we organize from our department, we will let you know. And please join the way. Please cooperate in the way you have done here. Okay, I'm concluding it. Thank you. I'm signing off. We'll get back to you. Be there in the WhatsApp group until we issue the certificates. Okay. Thank you. Thank you. Thank you very much.